Hi folks, and welcome to another episode of Open Analysis Live. So today I have something that's a little different. It's not a tutorial, it's just something that I discovered. I uncovered it looking into a bug, and I just kind of found this and I want to share it because I think it's really cool. It's just probably a useless piece of trivia, but I thought I'd make a little quick video and share it with you guys. So the way that this came about is a buddy of mine, Alex Hannell, he writes the Hooked on Mnemonics blog. If you guys don't follow it, I'll link it in the description below. It's an awesome blog. He's a great reverse engineer, and he also has a lot of cool tools too. So I'll probably link to his, he doesn't use GitHub, he uses like that other Bitbucket thing that nobody can figure out how to pull from. But anyway, I'll link to his tools as well. So he was writing a hooking engine to sort of defang some VB scripts and JavaScript stuff. One of the things he wanted to do is he wanted to stop the script from creating any processes, right? So he just wanted to basically, anytime the script tried to create a process, he just wanted to hook create process internal W and set the create flags to suspend the process so that the process would be suspended. And what he found was that anytime a process was started using ShellExecute, for some reason, his hook was still set, but the process would resume. And we were talking about this, like, why is this happening? Because his hooks were all right, everything was good, and the secret is basically that if you call ShellExecute inside the ShellExecute DLL, they actually create a process suspended first, and then they resume the thread later on for some reason. And I don't know the reason why. In fact, I'm hoping that maybe someone can explain why they would do that. But it has the effect of, if you hook in the API call tree, if you hook lower, so you hook create process, like something in kernel 32, create process W or something like that, or create process internal W, the lowest API hook that you can get in kernel 32, then it doesn't really matter if you suspend the process, because once that call returns back into ShellExecute will actually automatically resume the main thread for that process and resume it. So thus making your hook invalid. And I mean, it's crazy. I mean, if anyone's written a hooking engine and had to deal with this, and you're watching this, let me know let me know if you can tell me why they do this. And what I thought I'd do is I thought I'd just quickly show you guys in a video here. I'll just kind of show you the API call chain, so that if anyone here is not familiar with how that works in Windows, we can go through that. It'll be a nice little refresher. And then I'll just show you guys the code in ShellExecute, so you can see that, it actually resumes. And again, I don't know the reason why, I'm fascinated by these little quirks in the Windows internals, like why these things were done. So if anyone out there knows, definitely hit me up and let me know. So we should do a quick refresher on the Win32 API call chain, just for background here. So when you're writing code, if you make a call to ShellExecute, when you're writing the code, you might call it ShellExecute, but when it's compiled, it'll be compiled into ShellExecute A or ShellExecute W, standing for ASCII or wide string, depending on the arguments that you've passed into it. So you can call either one. If you want to use wide strings when you're writing your code, that's fine. If you want to use ASCII strings, that's also fine. You have access to both those APIs. However, internal to the DLL, if you call ShellExecute A, so Windows likes wide strings. So what they'll do is that internal to the DLL, they'll actually convert your parameters from ASCII into wide if you use like an ASCII call. So if you have ShellExecute A, you're passing an ASCII string in. Internally, they'll actually convert that over to a wide string, and then they'll call the wide string version of the API. Now here, there's one step further. We can see there's an EX call here first. So EX stands for extended, and it's basically an API interface to the same function that allows better or more descriptive arguments. So it's like basically think of it as like a better version of the API call, an extended call. So if you call just the basic call, internal, they'll always convert it into an extended call if there's an extended call available for that API. So it's kind of funny because you think you're calling ShellExecute A, but really what you're doing is first that's being converted into ShellExecute EXA, so the extended version of the ASCII call, and then again it's being converted into the wide string version of the call. So this all happens internal to the DLL. Now, we're not done yet though, because obviously Shell32 DLL doesn't create processes, right? It's an interface for you to write against. So it has to call into kernel 32 DLL, and it's going to call create process W. So since they already converted your ASCII strings into wide strings inside the DLL, so A for ASCII, W for wide, because they've already converted into wide strings, they call create process W, and then inside kernel 32 DLL, there's another conversion that goes on where they will call create process internal W. Now, create process internal W is not a documented API call, or it's not officially documented. There's lots of documentation for it, but not officially from Microsoft. Basically, when it comes to creating processes, this is the lowest level userland. That's a bad way to put it. I think of this as the as the lowest level userland API call that you can hook. Now, as you can see below, anti-DLL, which calls into the kernel, anti-DLL.dll is obviously userland DLL, and you can hook stuff in there as well. So you can hook lots of NT stuff, but it's probably easier to hook create process internal W, because I believe almost everything in userland must go through there. Whereas there is a couple different NT create process, NT create user process. So there's a bunch of different APIs in there which you'd have to hook. It's kind of funny. It looks like a funnel where everything funnels into like all these different create process type API calls funnel into create process internal W in kernel 32, and then they kind of funnel out into NTDLL, into a bunch of different calls there. I believe I might be not completely accurate with that, but basically this is how I think about the call chain for create process. Now, the reason why I have this little thing highlighted here, a bunch of question marks, is because when we call ShellExecute, we're not calling it to suspend the process, right? So we don't pass any suspend process flags in there or anything. However, if we were to hook create process W, we'll see that the process is actually created suspended. So somewhere in here in Shell32 DLL, they actually set the create suspended process flags for the process creation flags. Again, I'll show you all this in IDA. I'll show you in the disassembler. I just want to walk you through the chain so you're familiar with like how this works before we get into the actual code. So the question is, why are they doing this, right? This is, again, I don't know the answer to this. I know that they do it, and I know that once you return back, so once all these calls return back into Shell32, the next thing that they do after they call create process W is they call resume thread for the process. So they create it suspended, and then they resume it. And again, I looked through the code kind of briefly just to see if I could figure out why they do this, and I couldn't. So now that we have the call tree figured out, now we can sort of visualize it. I think what I'll do is I will just quickly talk about the create process flags, so that if anyone is not familiar with what those are, you'll be able to recognize them. So this is a documented version of create process internal W. And we can see down here, there's one of the arguments is creation flags. And if we go and look up the creation flags, we can see this is all documented on MSDNs. So if we pass in 4 in one of the flags, like if we set the 4 flag, then it'll actually create the process in a suspended state. And then you can call the resume thread function to resume it. So remember the create process flags, there's a whole bunch of them. So it's not going to be just 4 or nothing. It's going to be a large number. But if we look at just 4, we can see whether it's set or not. So I think that's probably enough to give you guys the background to see what's going on. And then right now what I think I'll do is I'll just pop over to IDA and we can do a quick walkthrough of this. So here we have our IDA instance, and you can see we're looking at a copy of wscript.exe. And this is because the test file that we're going to use to call ShellExecute is actually a script file. So if you look in the debugger here under process options, you can see we're going to call wscript.exe, and we're going to call it with this test.js file. So why don't I give you guys a look at the test.js file for right now. So we'll just open this up in Sublime Text. So it's really simple. It's just a JavaScript file. And we set the string calc.exe to command to run, and then we pass that into ShellExecute. So if this runs, it should just open the calculator. So let's double click on it, and we'll show you it does that. Here's the calculator down here. And so now let's run it in IDA. And what we'll do is we'll add some hooks to show you guys that the process is in fact started suspended. And then we'll look into why that happens. So what I've done is I've added a breakpoint on start. And the reason why I'm using the local debugger is because it's not a malicious script. So I feel safe running the debugger on the same VM that I have IDA installed on. Obviously, if this was malware, I would never do that. Don't want to lose that precious IDA license. Okay, so let's start this up. Once it gets going, what I'd like to do is I'd like to set a breakpoint on create process internal W, which is in kernel 32. So let's go over to our Control F. If you guys don't know this, in any window in IDA, you can type in Control F and it opens this little search bar, and then you can search for kernel 32. You can search for anything you want. It's super helpful. So if we come in here, we'll Control F for create process internal W. There we go. So I'm going to set a breakpoint on the start of this create process internal W, and then I'm just going to run the script, and hopefully we end up here on the breakpoint. Yeah, so we've hit this, we've stopped, and now what we can do is we can take a look at the arguments on the stack and see what the create process flags are. So here's the stack right here. Here's the return call. So this is the first argument right here. And let's go back and take a look at the definition here for create process internal. So the creation flags are 0, 1, 2, 3, 4, 5, 6 down on the stack. So let's come back over here. 0, 1, 2, 3, 4, 5, just a little bit lower, 6 on the stack. And the interesting thing about this, let's highlight it so you guys can see better. So you can see that that 4 is actually set for creation flags. And if you recall just a second ago when we talked about the process creation flags, if the 4 is set, that means to start the process suspended. So you can see that something's happened in between that JavaScript call just to create calc.exe and this call to create process internal. And basically something's happened to cause it to create suspended. So what I'd like to do is I'd like to hop back into ShellExecute, and I'd like to see why, or see where this is set. So a way to do this is to sort of use your run until return here. So we run until we return. Let's see where we are. We're in kernel 32 still. So remember that call stack. So we were here. Now we've gone up 1 probably into create process W. So probably the next return is going to bring us into ShellExecute. So let's see if we can do that here. Let's return one more. Run until return. All right, now we're in shell 32. Everything looks good, right? So let's take a look at this code here. Now, this is basically a loaded DLL in another process. I could go and try and analyze this and stuff, but what I'd rather do is just open shell 32 DLL in IDA, and because it's a Microsoft DLL, there'll be debug symbols for it. So what I'd like to do is open it with the debug symbols so we can get all the nice markup for the code and make it easy to read. So I'll stop this debug session here, and I'll pop over to the other IDA instance I have here with shell 32 DLL. And I've already loaded it up, and you can see it has the, obviously the debug symbols are loaded because everything is super well documented. Either that or I'm really good at documenting stuff. Yeah, it's the debug symbols. So here we can see this is an internal function that's actually called from ShellExecute. So this is internal to shell 32 DLL. And this is where create process is called. And I'll show you guys what's going on here. So here's our call to create process W, just like what we saw in the API calls here, right? Here's our call to create process W. So let's look and see if we can find in the code what kind of funny things are happening here. And it should have been, it's pretty apparent actually, because we're using the hexarrays decompiler, so we can actually see the C code or pseudo C code. So here's the creation flags, and they actually OR them with 4. So they add that flag, and then they pass that into create process W. So you can see that they're actually doing that to the process. There is this check up here, and if you were to look at this check, var 27, let's name that var check process flags. And let's go up and see where that comes from. So if we scroll up to the top, we can see that that's actually an AND with the creation flags. So this is kind of a neat trick that they do. If there's a call that comes into this function where the creation flags are already set to suspend the process, then this function won't reset those flags. So it'll pass them in. And we can see down at the bottom here, so they call create process with the creation flags set to 4. And at the bottom here, if the flags were not set when it came into the function, so if you weren't trying to suspend the process when this function received the call to create a process, it will actually resume the thread. So all the magic here happens inside this function, inside shell 32 DLL. So you can see they start it, suspend it, and then they resume it here. The question is why? So I'm not exactly sure why this happens, like I said. I could take a guess, though, that maybe this has something to do with starting the process and checking to see whether it needs to be run as administrator, or maybe something to do with like UAC prompts. I do see that there's a little bit of stuff going on here with the checking whether it should be an elevated process or not. I'm not sure why you would need to start it suspended and not just start it, because I think that you would still get these errors. You would still get the error code if you started it not suspended. Maybe they think it's a cleaner way to do it. I'm really not sure actually why exactly they would start it suspended and then resume. But my best guess is that right now is that it has something to do with checking whether the process needs to be elevated, and something to do with maybe with like a USC prompt or something like that. So again, I found this. I think it's really cool. I think it's interesting. And if you're writing a hooking engine, then you need to be aware of this. You need to be aware that you can't just set a hook down here at create process internal and suspend every process, because if it's called from ShellExecute, once it returns back to ShellExecute code, it's going to be resumed automatically. So just be aware of that. So again, I don't know why they do this. There's probably some interesting reason for it. So if you guys know why, let me know. Otherwise, I hope this has been kind of an interesting tidbit of information, reverse engineering trivia. So as always, keep exposing the mechanics behind the malware and stay curious.